We can say the same thing for the absolute minimum, right? Meaning if f of c is the absolute minimum, if, oh, that was my firewall. If every other point is greater than or equal to f of c, all right? So that's absolute minimum and absolute maximum. Okay, so take a look at this one. We have sine of x and cosine of x on the interval negative pi to pi. We want to find the maximum and the minimum. And this, this is stuff that we already know, right? So the maximum is here, but how do we write it? We say, okay, so the maximum value is what? Maximum value, that's the y value. Maximum value is the y is 1. And where does that happen? At pi over 2. So I say the maximum is this. F of pi over 2 is equal to 1. Yeah.
I thought, what is the thing that said that, like, what's the difference between maximum and minimum values and relative maximum?
Okay, we're going to get through all of that in this lesson. Yeah.
Isn't the maximum, like, on the interval of negative pi to pi, it's f of pi over 2 is 1, but isn't, like, if we didn't restrict the domain, it would be like pi over 2 plus or minus 2 pi.
But right now, so in calculus, it's very rarely over the entire domain. Most of the time, we have a very specific domain. All right, and so this is the maximum, and so the minimum then is this point, and we say f of negative pi over 2 is equal to negative 1. All right, so that's the minimum. Here, we have a maximum at 0, so f of 0 is equal to 1. And then for the minimum, right, look, we have two minima here. Right? And it's f of pi equal to negative 1 and f of negative pi equal to negative 1. Okay? All right, let's go talk about absolute maxima here. All right. Okay, I have here different domains, and given each domain, we have to talk about absolute minimum and absolute maximum. So take a look here. When the domain is negative infinity to positive infinity, so the entire life of this parabola, right? This is f of x equals x squared. Well, let's do minimum first, because that's easier, right? The minimum is f of 0 equals 0. Is that right? Okay. How about absolute max? Yeah.
They're going to keep going out, so like
there is no, exactly. There is no absolute maximum that it ever reaches, right? So there is no absolute max because it just keeps, even if you're at the highest point, there is still a higher point, okay? Now, here, okay, so the rest of these are very, very important. Now, if I go from 0 to 2, 0 to 2 inclusive, okay? Here I have very, very clearly defined boundaries. In this point, the highest point, the absolute maximum is f of 2 equal to 4. And the absolute minimum is f of 0 equal to 0. Okay, now when I have 0 to 2, but 0 is open, right? And it's just that region. Well, I have an absolute maximum, right? That's f of 2 equal to 4. But there is no absolute minimum, right? Because this is open, it just sort of like hangs there. So you can't say, like, what are you going to say here? F of, what, 0.9? But then there is f of 0.7. But then there is f of 0.01. But then there's f of 0.0001. So there is no, you cannot define that point, right? So the absolute min is none. Similarly, if I now leave both of them open, right? It's the same argument. There is no absolute min, there is no absolute max. Okay? All right. Okay, so look at this here. Here we're saying a function may fail to have a maximum or a minimum value. Yeah, it may. But if I had my intervals closed, is it possible that a function does not have an absolute minimum or an absolute maximum? That's not possible. When the interval is closed and it's a continuous function, then it is not possible for something to not have a minimum, an absolute minimum, or an absolute maximum. Okay? All right. Okay, extreme value theorem. Okay, so we've gone through a couple theorems until today, the mean value theorem and so on. And we've seen that each one of those, they may seem a little like overwhelming at first, but once you really look at them, it's all like, oh my God, yeah, like duh sort of things, right? So exactly. So look at the extreme value theorem. It says if f is continuous on a closed interval AB, right? And so now you're saying that when we learned what it means to be continuous and differentiable, it wasn't just so I could give you problems and say, is this continuous, is this differentiable? No, it's because those are now going to become hypotheses of our statements. Okay, so if f is continuous on this interval, then f has both a maximum value and a minimum value. Think about that for a minute. Think about that in relation to here. If f is continuous like this function on the closed interval a to b, like this one, then there must be an absolute minimum and there must be an absolute maximum, right? Just like the example we just did. So again, it's like duh, right? It starts somewhere, it goes somewhere, it's continuous. There is a lower point, there is a higher point. Okay, now for the big deal. How to find absolute maximum and absolute minimum values. All right. Step one, you have to find what we call critical points. Okay? Now, you also have to make sure that once you find the critical points, that they're in the domain. So sometimes you do the math and you say, okay, these are the critical points, but then you realize, oh wait, but I'm given a totally different domain which doesn't apply here, right? So you have to be careful. Okay, what is a critical point? This is important. A critical point is a point within the domain of the function, within the domain, 0 to 2, a to b, where two things happen. One, either of two things happen. Either f prime is equal to 0 or f prime does not exist. All right? So those two will qualify as a critical point. It doesn't have to be both. One is okay. Okay, so first we find the critical point. Then we evaluate f of x, and I can't stress this enough, evaluate f of x at each critical point. And now the largest value is the absolute maximum, the smallest value is the absolute minimum.
F prime does not exist. An example that would be like if it was like going like that.
A cusp, right? Not differentiable, a cusp.
The cusp could be the minimum. If it just keeps going outwards.
So you can't really define it that way because that's, yeah.
Infinity.
Yeah.
Could you show us this on the previous problem that we just
We're going to do like 50 problems. Yeah, we're going to do so many of them. So look at this one. In summary, extreme values occur only at critical points and endpoints. So here, step two, I stressed this, but I didn't stress these. So when you evaluate f of x, you have to evaluate it at the critical point and both of the endpoints. Okay? All right. Okay, yeah.
But if it's like in the previous example, where it was like closed on one side and open on the other. Is that still valid there, but even though it's not continuous?
No, let's do a couple. And you'll see. Okay, so look at these. So these are a couple of examples. Each of these functions are shown on the interval a to b. And so you see for the first one, you have absolute maximum and absolute minimum, right? And they're in the interior of the interval. Those occur at critical points. Now look at these two. Those occur at endpoints. So these are at the endpoints. These occurred at the critical points. Let's do a few examples and you guys will know exactly what I'm talking about. Okay, so use analytic methods to find extreme values. So basically use the calculus you know and find them, not graphically. So what we need to find is the extreme values of the functions on the interval. Yeah.
So then, will the extreme values be where we can't find either 0 or if it's 0?
That's where f prime is 0. It can be there, or it could be at the endpoints. Okay? It can be there, or it can be at the endpoint. Okay, so here's what we're going to do. First, we have to find the critical points. What did we say about the critical points? It was where f prime is 0 or it doesn't exist. That means first we have to find f prime. Okay? So let's find f prime of x. F prime of x is equal to negative 2x plus 4. So step 1 was find the critical point. Right? So you do that with the derivative. Okay, so is there a point, where is this 0? Well, let's see. 0 is equal to negative 2x plus 4. X is 2. That's a critical point. Now, yeah, so hang on. So now, is there a point? So this is where this derivative is 0. Is there a point where this derivative is undefined? No, because negative 2x plus 4 is defined everywhere. So, okay, so we move past. We're going to do millions of them. Well, maybe 4, but I'm going to do a lot. Yeah. Okay, so step 2 is evaluate f of x at each critical point and both endpoints. Okay, so step 2. We say, okay, so we evaluate it at the critical point. So we say f of 2 is equal to, and then, you just like, it's negative 2 squared plus 4 times 2 minus 5. That's negative 1. Okay, that's f of 2. But then we also have to evaluate it at the end points. What are the end points? 0 and 3. So f of 0, and we get negative 5. F of 3, we get negative 2. Now, these are the y values. Negative 1, negative 5, negative 2. The one with the highest y value is the absolute maximum. So here, this is the absolute maximum. And this is the absolute minimum. Huh? I plugged 0 into f. I got negative 5. Okay? Right. So you find the critical points, and then you have to plug in the critical point into f, the end points into f, and then the highest value is your maximum, the lowest value is your minimum.
So how would you express that?
That's it. So you just say absolute max f of 2 equals negative 1, absolute min f of 0 is negative 5. Okay, let's do another one. So first we have to find the derivative. So yeah, so f prime of x is equal to 2/3 x to the negative 1/3, which means it's 2/3 cube root of x, right? Okay, so now you ask yourself, where is f prime equal to 0? Nowhere, right? If you have a rational function, how do you see where it equals 0? You basically set the numerator equal to 0. But the numerator is 2, it's never 0, so never. So that's not possible. And then you say, where is f prime undefined? It's when the denominator of f prime equals 0, right? So that's at x equals 0. So that is now my critical point. Okay? Next, I have to evaluate f of 0, f of negative 2, f of 3. Yeah.
So is the first step always to do when is f prime equal to 0?
First you find f prime, and then you ask yourself, where is it 0, where is it undefined? Okay?
So
Either. It doesn't matter. It doesn't matter because you have to take both. Yeah.
Just like say for that one, you know it's a cusp.
Uh-huh. Uh-huh.
When you still have to find the derivative, or can you tell?
Yeah, you have to show your work. You have to justify your work. Yeah. It is, yeah, and then you have to show it with the derivative though. So f of negative 2 is the cube root of negative 2 squared, right? Which is what?
You can't have the cube root of 0.
The cube root of 0 is 0. What number multiplied by itself 3 times gives you 0? So this is the cube root of 4, which is fine as the cube root of 4. And then here I have the cube root of 3 squared, which is the cube root of 9, and that's just the cube root of 9, right? So 0 is clearly the lowest point, so that's my absolute min. And then if I'm comparing cube roots, we go with the radicand, right? Cube root of 9 is higher than cube root of 4, so that is my absolute max.
Why didn't you exclude the 3?
Huh?
Did you divide by 3?
Which 3? Okay.
You're not plugging back.
So this, you evaluate the function, the f of x, because, okay, what this does is look for the x values where this will occur. But then you want to look for the highest point and the lowest point of the function. So you evaluate it in f, not f prime. Yeah. Mm-hmm. Oh, yes, there can be. We're going to do some examples with that too. Yeah. Okay. F of x is e to the negative x. So f prime of x is negative e to the negative x. Right? Which is what? Negative 1 over e to the x. Okay, so here's, okay, if you have a fraction, now you have to see, is f prime of x ever 0? So if you have a fraction, look at the numerator. Is the numerator ever 0? No. How do you check if it's undefined? Undefined is where the denominator equals 0. So where is e to the x equal to 0? Never, right? So f prime of x is never 0. F prime of x is never undefined. So you say there are no critical points. Right? So then we're just left with endpoints. So now we're going to do f of negative 1, f of 1. So f of negative 1 is e to the negative 1, which is e. F of 1 is e to the negative 1, which is 1 over e. So absolute max, absolute min. Okay, now let's do relative extrema. Okay, this is what you guys were asking about before. All right. So we either call them local extreme values or relative extreme values. They mean the same, right? So the figure below shows a graph with 5 points where there are extreme values. So extreme values are either, maxima or minima. Okay? So look at this one. Let's look at the maxima, right? So this looks like this is a maximum. This is a maximum. The highest one is an absolute maximum. The other is a local maximum. All right? Yeah, we did do it last year. We did it a different. We just did it like this. We did it conceptually, but we never did it using calculus, obviously. Okay, and now look at the minima. I have a minimum point here, right? Because it's going down. I have a minimum point here. Clearly, that's a valley. And then I have another minimum point there. And so the lowest is the absolute minimum. This is a local minimum and then another local minimum. Okay, now look at this one that I called absolute minimum. That's an end point. The reason why it could qualify as an absolute minimum is because it's a closed interval AB. Okay? All right. Correct. It wouldn't be anything. Okay, so what are relative extrema then? So if C is in the interior of a function, is in the interior of a domain. Okay, there is a local maximum if there are some f of x, if there are some values which are lower than that value in some open interval. Okay? Let me say that another way. Something could be considered a local maximum if there are any other points which are lower than that. And that makes sense, right? Something can be considered a local minimum if there are any values that are in any way higher than that. Okay? All right, this is the important one here.
So any point could be a local maximum if you restrict the interval.
No.
Not any.
Yeah. Well, and like a constant function. Okay, yeah. Okay, so a function has a local maximum or a local minimum, right? Okay, so if a function has a maximum or a minimum value at an interior point, and if f prime exists, then f prime of C has to be 0. Let's think about that for a minute. In an interior point, right? If it's an interior point and something is a local maximum, not an absolute maximum, a local maximum, that means it looks like something like this. That means it has to be lower before, so it's increasing to that point, and then it has to go back down, right? Otherwise, it would be like an absolute maximum, right? Well, in order for that to happen, it has to turn around, which means over there, f prime of C has to be 0. There has to be a 0 derivative. Okay? So if this were to be a local minimum, a local maximum, not an absolute maximum, a local maximum, there has to be some points lower than that, so it's increasing to that point. But then it can't increase indefinitely because it's only a local maximum, it's not an absolute maximum. That means it has to turn back around. Well, anytime it turns back around, there is momentarily a 0 tangent there. Isn't that cool? That means if there is a local maximum, then f prime of C is equal to 0, right? Add also, or f prime of C is undefined. Yeah.
But what if, like, so for the example above, like for the absolute maximum, it also still has a tangent to 0, right?
Oh, that's fine. That's fine. An absolute
How
maximum
do you tell? Can you look
could be.
analytically?
Oh, wait and see. Yeah.
So, like up here, like up here, it would be f prime of c is 0,
Uh-huh.
not undefined because.
Correct. Yeah, but on the other one, it's, so like if that other one, so if this was an absolute, if there was a point even higher than this,
Oh, that
this is where f prime is undefined. Okay, so let's do a couple. When does this class finish?
11:50.
Oh, good. We have time. Okay. Any questions? Okay, so here's how, what were you asking? So here's how you can tell analytically if it's a local maximum, if it's a local minimum, and so on. Okay, so what have we learned so far? We've learned that if it's a closed interval and you want to find absolute max or min, you find the critical points, and then what do you do for the closed interval?
You take the,
After you find the critical points, what do?
you take the endpoint.
Find the one. Find that
You
one.
have to plug everything back into f prime, okay? This is a thing. Okay, so now, suppose there was a question on the test, and like you knew just by looking at it, this is where the absolute maximum, this is where the absolute minimum is, and you don't show me the points where you plugged it in, I have to take points up, even if in the end you gave me the right answer, right? Because it's part of your justification. This is AP. You've got to I take that back. Even at level, I take points off, right? Because that's the process. Okay. Mm-hmm.
So for the local extreme values, this, so is it just for, I know that says this is also a local maximum, so can that also be for this, like the absolute maximum, like the f prime of that is undefined?
Okay, so here's how you find local extrema. First, you have to find the domain. That's important, right? Because if there is an asymptote, let's say a vertical asymptote, then you have to take that into consideration. Then you have to find the critical points, and you find the critical points the same way every single time. Make sure the critical points are in the domain. Okay, then we have to create a number line. All right. And then we have to see where things switch back and forth. So here's what I'm going to do. I'm going to actually solve this example, right? And then you can compare with the steps that I've written down here. But what were the first things? First was find the domain. So here is a function here. This is a polynomial function. What's the domain of this function?
All your numbers.
Right. Negative infinity to positive infinity is the domain. All right, that means all points are values where the graph is defined, or the function is defined.
There's no absolute maximum.
Yeah, no, absolute maximum.
Right, because it's continuously. Okay, so let's do this. F prime of x is equal to 3x squared minus 6x plus 3. Right, and to find the critical points, I have to set this equal to 0. Let's factor out of 3. And so that the 3 will go away, right? So I have x minus 1 squared is equal to 0. So x is equal to 1. That's my critical point. Okay, now what I'm going to do is this. Look at number 3. Create a number line and label the critical points and any endpoints. So let's do a number line. I only have one critical point, that's a 1. And then I like to put in my domain here. Like here, it goes all the way to negative infinity and positive infinity. Okay, now what we're going to do is this. Using the number line, test values within each interval. Here's the important part, guys. We have to plug them into, f prime of x. Okay, so let's pick 0 from here. If I plug it into f prime of x, do I get a positive or a negative value? Positive f prime here.
Oh,
You get positive.
oh.
If I pick the 2 and I plugged it in there, what do I get? Still positive. Okay, here we go. This represents f prime now. What's another word for f prime, like an algebra 2 word for f prime? Slope. Here, f prime is positive, which means slope is positive. What does that mean about a function if the slope is positive? What is it doing? It's increasing. So here, if f prime is positive, f is increasing in that interval. In the interval next to it, f prime or slope is positive. It means what is f doing? F is still increasing.
There's no absolute.
Right. Now, because this is just continually increasing, it never turns around, then there are no absolute values. Okay? I'm sorry, no extreme values. So even here, when it's like the lowest point, there is no lowest point because it's always going down. And then to the right, if it's increasing, there is no highest point because it's always just increasing. There's always a higher point than where you're at. Yeah. 0. Yeah. Let me do the next 2 and then it'll like solidify. Okay. Look at this one. First we have to figure out domain. So the deal with this is the denominator can't be 0 and the radicand can't be negative.
It can be negative 2 or positive.
Well, so the thing is 4 minus x squared has to be greater than 0, right? So remember how we did this? It was 2 minus x, 2 plus x greater than 0. And if it's a nonlinear inequality, then I have to test values. So negative 2, positive 2. And if I have a value from the middle here, like 0, and I plug it in here, I get positive. And then do you remember using multiplicity? This is going to alternate. So it's negative, positive, negative. So if I want the radicand here to be positive, then I have to pick the region from negative 2 to 2. So the domain is negative 2 to 2.
Why is it not restricted? It's not closed.
Because it can't be 0 either, because it's in the denominator.
No absolute.
Okay, so hang on, let's do this one.
Why is it closed?
Because if it was closed, then if x was 2, then in the denominator you get 1 over 0. And you can't have 0 in the denominator. Yeah.
So the reason we need negative 2 to 2 is because.
Oh, sorry, this one is also negative. This one is also negative. Yeah. Okay, now, so let's find f prime of x. So f of x is 4 minus x squared to the negative half. F prime of x is negative 1/2. 4 minus x squared to the negative 3 over 2 times negative 2x. The negative half and the negative 2 go away. So all I'm left with for f prime of x is what? X over to the 3 over 2. And let me write it, well, let me write it this way. Okay, now, this is like critical point heaven here, because where are my critical points?
Negative 2 and 3.
Well, okay, so first of all, where is f prime of x equal to 0? Okay.
It's when the numerator is equal.
There we go. Okay, I really need, I really have to stress this part. It's very important that you guys understand this. When you have a rational function, this rational function is 0 where the numerator is equal to 0. So f prime of x is equal to 0 at x equals 0. So that's one critical point. A rational function is undefined when the denominator equal to 0. F prime of x is undefined when 4 minus x squared is equal to 0. X is plus or minus 2. I just extracted 3 critical points. Are all of them within my domain? No, only the 0 is within my domain. So, I do my number line. The only thing I could put in is 0. Here, it's an open interval, right? This is -2 and 2, but it's an open interval. That is not included in my domain. So now, because I can't also go beyond -2 and 2, I do kind of put my little barriers there, but I make them open barriers. Okay, now, in the first region to the left, if you pick -1 and plug it into f prime, okay, so this is the cube root of something squared. The denominator is always positive. And then so if x is negative, then the numerator is negative. And then where x is 1, this is positive. So that's f prime. Well, what about f then? If slope is negative, f is decreasing. If slope is positive, f is increasing. So 0 is a minimum. Okay? Yeah, relative minimum or minimum, it doesn't matter. So, but it's not an absolute minimum. Okay, so now we say there is a minimum here, right? There is a minimum, but where is it? The minimum is at x equals 0, but what's the y value? You have to plug it in. So now f of 0 is 1 over the square root of 4 minus 0 squared, 1/2. So there is a minimum f of 0 equal to 1/2. Yes, sir.
How would you know if it's a minimum or a maximum? I understand you know that there's...
So let's look at the critical points.
Is that 1? Because that's
Okay. Well, first, what's the domain here? Uh-huh. Okay, so there is a division at 1, but now at 1, is there a situation where this is undefined at 1? No, at 1 this is a defined value. That's fine too. So it's -infinity to +infinity. Because where one function ends, the other one just picks up, so it's all good. Had this also been open, then we would have had to split it up there. Okay, so now let's find f prime of x. So if this is a piecewise function, f prime is also going to be a piecewise function. And it's going to be -4x and 1. Okay, what about the regions though? This is going to be -4x at x is less than 1. So remember, at x equals 1, is the function differentiable? Is there a derivative at x equals 1? What's the derivative at x equals 1 for the top? -4. What about for the bottom? 1. So at x equals 1, this is not differentiable. That means the derivative can't exist at 1. So when you write the derivative, it has to be open at 1. My strokes. Okay. Now, let's do critical points. Where is f prime of x equal to 0? Well, the bottom one is never 0, but the top, 4x equals 0. So x is 0. So that's one critical point. Okay, where is f prime of x undefined? Not at 1?
Oh, okay.
Right? Okay, so look, f prime of 1 from the negative side is equal to negative 4. F prime of 1 from the positive side is equal to 1. So at x equals 1. So now I have 2 critical points. Yeah.
Why did you get rid of the square that
Because the derivative, okay, so at the end, if it's an endpoint, the derivative can't exist there anyway, right? Because it stops abruptly. And plus, like if you see from top to bottom, the derivative isn't the same, right? So it can't, the derivative can't be defined at that division point.
Can some derivatives be defined?
No. No. Yeah. Okay, so here we have negative infinity and positive infinity again. All right, so go ahead and plug points in. So at negative 1, we're in the top region. The derivative is positive. At like 0.5, it's negative. Oh, yeah, negative. And then it's positive here because it's always 1. Okay, so now the function is increasing, decreasing, increasing. So there is a maximum here and a minimum there. Okay. Yeah. So, but while I take that question, go ahead and plug in f of 0 and f of 1 and find the maximum. Okay, so look, f of 0, we plug it into the top one, 5 minus 2x squared. So it's 5 minus 2 times 0 squared. That's 5. And then f of 1, I plug it in the same one. I get 3. So here, these are my max and min, right? So I say max and min.
Why don't we choose to use the 5 minus 2x squared?
Okay, so we have to plug it into f of x, a. And then if I am plugging in x equals 0, I go to my regions. X equals 0 falls in the top region, so you have to plug it in there. X equals 1 also falls in the top region, so I plug it in there.
What if these weren't continuous?
If they weren't continuous, then at x equals 1, there would be a break in the domain. So there would be like one additional region. Yeah. Okay, so this homework is due when? Monday? This homework is due Monday. Monday we meet last period. A period is last. So this homework is due then. And then Monday, I'm going to cover section 2. Here you're going to use the extreme value theorem for these. Okay?